Hello my dear viewers, this is your math and chem tutor back again with this video. Now before we dive into this, I would request that you follow me on TikTok with the same name, math and chem tutor. Then consider subscribing to this YouTube channel if you have never done so. Like this video, share it, you can share the link. Contact me on these numbers to find out anything that you might be inquiring about. Let's dive into this lesson. Now, the lesson for today is factors affecting the melting points and boiling points of different substances. Now, when we refer to a substance here in chemistry, we are referring to the category of a metal, a non-metal, a semi-metal, covalent compound, or ionic compound. Now, before we dive into this, let us first define what we mean by melting point here. Melting point is the constant temperature actually at which a pure solid and a liquid are in equilibrium with each other, because as the solid melts, it melts to a liquid, then it must do so at a constant pressure, at a constant atmospheric pressure. The atmospheric pressure we are referring to, the standard one, is actually 760 millimeter mercury, or 1 atmosphere, or 101,325 pascals or Newton per square meter. So, alternatively, we can define melting point as a constant temperature at which a pure solid changes to a liquid state at a given pressure. So when the equilibrium has been established. Now, to understand further, we know that melting point of a solid is the same as the freezing point of its liquid. That's very true. For example, in water, ice melts at 0, and also liquid water freezes actually at 0. Now let's also look at the word boiling point here. Boiling point of any substance is the constant temperature at which its vapor is in equilibrium or equals the external atmospheric pressure, which we said it's 760 millimeter mercury, that is at sea level. Of course, it would differ at other levels. Now, this area of melting and boiling points is a challenge to students. So let's dive into the factors affecting the melting points and the boiling point of substances. Now, I've categorized down each substance on its own for students to understand better that when they are approaching these questions, when you are handling metals, you base on the factors for metals. When you're handling non-metals, you base on the factors for non-metals, and so on and so on. Let's dive in these metals here. Now, under metals, we have basically about 3 factors that affect the melting points, and basically all these factors are affecting the strength of the metallic bond. That's why we are emphasizing that they are actually indirectly affecting the melting point of the substance. So any factor that affects the strength of a metallic bond actually affects the melting point of that substance or the boiling point of the substance. Now let's look at atomic radius here. Atomic radius actually affects the bond length. When the radius is large, then the bond length is long, and if the bond is long, then it's weak. So bond strength reduces. Now looking down at the number of electrons contributed towards the metallic bond. Now this factor can be used to compare between 2 different groups. For example, you can compare group 1 elements to group 2 elements. We realize that group 1 elements have only 1 valence electron, so they contribute 1 electron towards the metallic bond formation, and group 2 contribute 2 electrons. So the metallic bond in group 2 are stronger than the metallic bonds in group 1 elements, giving group 2 elements a higher melting point. Now atomic radius can be used to compare within the same group or to compare different groups. Let's look at the third factor here, the third factor affecting melting points, called the type of crystal structure. Now, all metals have what we call giant metallic structures, and the giant metallic structures have divided into these common groups, which we are calling the crystal structures. Now, the first one is the hexagonal close-packed structure, face-centered cubic structure, body-centered cubic structure, simple cubic structure. Now, every type of metal, right from the S and P, the S block elements, up to the time you reach the transition elements, you realize that they adopt one of these structures here. Now, the only thing that we need to notice about these structures is that they are quite broad, but we can't go into that work because it might not be within the scope of our coverage to understand it further. Now, what we need to just know about these types of crystal structures is actually we are looking at the key thing called the packing of the atoms. How close are atoms packed in these type of elements? That HCP and FCC have a packing efficiency of 74, then BCC has a packing efficiency of 68%, then simple cubic structures have a packing efficiency of 52.4. So we are saying that all elements whose atoms are packed in hexagonal closely packed form or FCC form, they will actually pack close to each other up to around 74%. So it means the atoms are very close and the metallic bond is very strong in HCP and FCC, followed by the 68% in BCC. Now, this factor is only going to be important to us under the discussion of group 2 elements. So keep that in mind. We shall not dive into much, but we are only emphasizing packing efficiency that affects the strength of the metallic bond. Let's dive into something else here. Now let's look at nonmetals here. Nonmetals and covalent compounds are both called molecular substances. So we are basically first looking at nonmetals here. Now nonmetals they are affected by about the 3 key factors here. Molecular size. Actually, molecular size in the periodic table depends on the atomic radius of the atom. So when the molecular size is large, then there is a large surface area over which there can be formation of intermolecular forces. So the intermolecular forces would be many, and so the melting points or boiling points would be higher. Now, molecular mass here, when the molecular mass is large, of course, it increases the strength of the van der Waals forces, and so increases the leading to higher melting points. Also, the intermolecular forces, the strength of the intermolecular forces. Basically, for nonmetals, we are going to be emphasizing on van der Waals forces. We are aware that there are 2 types of intermolecular forces: hydrogen bonds and van der Waals forces. But basically, for nonmetals in the periodic table, they are basically bearing on the van der Waals forces. If the van der Waals forces are stronger, then we actually look at those elements or molecules having a high melting and boiling points here. So basically, these are the key factors for nonmetals. Let's dive into semimetals. Semimetals, we are going to only emphasize group 4 here. Group 4 in the periodic table. Basically, group 4 is a mixture of metals, semimetals, and the nonmetals. So you see that carbon is a nonmetal, silicon and germanium are semimetals, and germanium. Then tin and lead are actually metals. That means that here the factors that are going to affect discussions of melting points in semimetals are actually atomic radius, then type of bonding, then the crystal structure here. Now, the atomic radius is going to basically used to explain the first elements here, as we are going to see later. They are going to actually be having what we call the giant covalent or giant atomic structures. So they will basically be affected by the atomic radius, their bond strength here. Then also, being that it's a mixture of metals, nonmetals, and semimetals, the type of bonding in the structure that they are adopting will also be important. That the first 3, carbon, silicon, germanium, will actually have covalent bonds, whereas tin and lead will have the metallic bonds. So the type of bonding is actually important here. Then we say the type of crystal structure. Of course, we are saying that carbon, silicon, germanium will have giant covalent or what we call giant atomic structures. Then actually the tin and lead will actually have what we call the giant metallic structures here. So we shall base on those factors here. So for covalent compounds, of course, we say the molecular substances are either nonmetals or covalent compounds. So for case of covalent compounds, we are going to look at intermolecular forces. We've already explained that if the intermolecular forces are strong, then the melting points are actually high. Then we shall also look at the molecular size. Molecular size is actually dependent on the size of the atoms that form these compounds here. For example, if you look at carbon dioxide, you'll have oxygen and carbon. So the size, the atomic radius of those atoms in there can be used actually to predict the size. And so if the size is large, we say there is a large surface area for formation of the intermolecular forces. Then there is molecular mass here, molecular shape. Shape we are referring to either these compounds have linear molecules or they have branched molecules. If the molecules are linear, then there is actually they pack efficiently. But in case there is actually what we call in case there is branching, then there is spaces between the molecules. That one is very, very key about the molecular shape there. Then polarity, some molecules are polar. For example, if you are comparing propanone to an alkane, propanone is polar, but alkanes are not actually polar. So when you are comparing molecules that have some kind of high electronegative atom, then polarity would be spoken about here in case we are comparing the boiling points here. So to go back to point 1, intermolecular forces for covalent compounds are going to be divided into hydrogen bonds and van der Waals forces, not like for nonmetals where we have only van der Waals forces. Here, because some compounds contain hydrogen in them. Okay, let's dive in something here. Now for ionic compounds here, ionic compounds are those formed from ionic bonding containing a metal and a non-metal. So they are affected by what we call ionic radius, ionic charge, then the nature of the ionic compound. Nature we mean either the ionic compound is more covalent or more ionic, dependent on the polarizing power of the cations that are found in them. Now let's look at point 1 here, ionic radius here. When the radius is small, we know that the electrostatic forces are very strong. So for example, if you are comparing the melting point of maybe you are comparing the sodium oxide and lithium oxide, you realize that the ion of sodium is actually larger than the ion of lithium. So ionic radius is very, very key here, because when the radius is large, then the force of attraction are very weak. Of course, the electrostatic forces of attraction are actually the ionic bond we are talking about here. Now, ionic charge here is also very, very important. For example, if you are comparing magnesium oxide, say maybe you are comparing it with sodium oxide here. Sodium oxide. You realize that magnesium has a charge of 2+ with the oxide 2-, but sodium has a 1 charge, then the oxide is 2-. So we realize that the force will be stronger in magnesium oxide than sodium oxide. So charge is very, very important. Now, nature of the compounds, we are saying that here we are basically emphasizing the polarizing power effects of the cation and also the polarizability of the anion. So here I hope you get right what we mean by a cation polarizes the anion, then the anion is polarizable. I hope that one was discussed under what we call under the discussions of ionic bonding. Which factors affect polarizing power and which factors affect polarizability. Maybe briefly, when the cations are small, then they will have a high polarizing power, with also if their charge is large. But we realize that for the case of the anion, if the anion is actually big and has actually high charge, it is highly polarized. So the compound formed, like for example, if you are comparing maybe magnesium oxide and magnesium chloride, we realize that chloride ions will be highly polarized, making magnesium chloride more covalent than magnesium oxide. So magnesium oxide would actually have a higher melting point because the oxide anion is not highly polarized. Now, important points to note here that most times when they are setting questions, They might not set only metals, but they can set a period. For example, they can set a period 3, where you have period 3, where you can have running from sodium until you reach argon in the other side. So you'll be traversing from the metals through semi-metals until you reach non-metals. So because these questions are always confusing, we are saying that the students should put special attention on actually the factors for metals alone and the factors for semi-metals, then the factors for non-metals. And the student is required to talk about the type of structure that such elements adopt. For example, if you are traversing from sodium to magnesium, you talk about sodium and magnesium and aluminium having giant metallic structures. Then for nanometals, they will talk about simple molecular structures. Then when you reach like silicon, then those semi-metals actually have two types of structures. They have giant atomic structures or giant covalent structures, and also have giant metallic structures, for example, group 4. Now, some questions involving compounds, they can mix for you ionic and covalent compounds. So, attention should be paid very, very much. Also talk about the type of structures, like ionic compounds adopt giant ionic, covalent compounds adopt giant covalent structures, though that point is not here. Also, attention should be put on the factors for each of them. Ionic compounds have their own factors such as ionic charge, ionic radius, nature of the compound. Then covalent compounds also have their own factors such as the molecular mass, molecular size, etc. Let's dive into the questions. The first question here says the boiling points of some chlorides of period 3 elements are shown below. So these are chlorides that are found in period 3. So we traverse through the periodic table across period 3. We realize that sodium, magnesium, and aluminium are actually metals. Then silicon lies in the group 4 where it is actually semi-metal. So sodium being bonded to chlorine, this will be ionic bond, even ionic bonding. This would be expected to have ionic bonding, but because of the high charge density or the high ionic charge in aluminium and small ionic radius, make it to actually be more covalent and adopt a layered structure in this type of molecule here. So if you draw the structure of aluminium chloride, which is a dimer, it is actually a layered structure. So we realize that its structure actually has covalent bonds because it is actually more covalent. So here there is no ionic bonding here. So the structure adopts a layered structure with basically more of it being covalent. Silicon here. Now, how do you know the type of structure here? So this is a covalent compound, that's point 1. So it has covalent bonding. Then 2, being that it's a liquid, then it has simple molecular structure. So simple molecular structures are basically for liquids and gases with some few solids. Of course, there are a few exceptions here. So you are going to emphasize ionic bonding in sodium chloride and magnesium chloride. Then emphasize what we call more covalent character here. Then here emphasize simple molecular structures with weak van der Waals forces here. Okay, so you can look at the solution and we discuss through. So we say that the melting points actually were decreasing from sodium to magnesium to aluminium to silicon 4 chloride. So because these are there are only 4 compounds, you can move from each. Can give a general comment. They decrease from sodium to magnesium chloride to aluminium chloride to silicon 4 chloride here. So we saw that it is a decrease, but the decrease, we would expect that sodium chloride would have actually a lower melting point because it has a charge of +1, then magnesium has a charge of +2. But here the key factor now that is going to come in here is actually the polarizing power of the cations of magnesium and the sodium ion. Now, sodium chloride and magnesium chloride have giant ionic structures. So we emphasize that if you are given compounds, a mixture, so mention about these structures. They are held by strong ionic bonds, which require amount of energy to break. That one is known that ionic bonds are actually stronger than covalent bonds. Then the decrease in magnesium. Why magnesium chloride has a lower melting point? Because magnesium ion has a small ionic radius, high polarizing power, so it greatly polarizes the chloride. So sodium ion actually has a less polarizing power. So magnesium chloride would actually be more covalent, and the sodium chloride will be more ionic. That makes magnesium chloride less stable. Now diving into aluminium here, aluminium chloride here has a lower boiling point than both of them, because actually for it we said it has a high charge density. So the aluminium ion is highly polarizing, so it polarizes the chloride ion, making the compound actually very, very covalent and thermally unstable. Silicon 4 chloride, we said it's a liquid, so correct this. Silicon 4 chloride, at that point here there is a correction, has a simple molecular structure. So because a liquid, and liquids actually have they're actually having simple molecular structures, and they are joined by weak van der Waals forces. Though within the molecule there are covalent bonds, but from molecule to molecule, silicon 4 chloride to another silicon 4 chloride will be van der Waals forces here. Now looking at another question here, number 2. The table below shows the boiling point or melting points of halogens here. So they have given us boiling points and melting points. They wanted us to plot a graph here. So we can look at the graph here. So we see that generally, if you plotted, make sure you plot on the graph paper. This is just a sketch. So the boiling points and melting points, all of them rise. And remember that these are all nonmetals, and the factors for nonmetals, we said they are basically 3: molecular size, molecular mass. Then we also say the strength of the van der Waals forces. Now, since if we look at fluorine, all the elements are diatomic. Fluorine would actually, if you get their molecular masses, like chlorine is 35.5 times 2, you get 71. Bromine is about 80 times 2, you get around 160. Then iodine is 127 times 2, you get around 254. So the molecular masses are increasing, and so also since atomic radius increases down the group, also their molecular sizes are increasing. So the strength of van der Waals forces increase. So basically here you are using those factors for only nonmetals here. So you can have a look. Boiling point and melting point increase from fluorine to iodine. That is true. Because atomic radius, because we said for nonmetals, the molecular size is because the radius increases. Then molecular size increases, molecular mass increases, magnitude of van der Waals forces also increase. So which actually increases the boiling and melting points for these elements here. Let's look at question 3. So in question 3 here, we have a mixture of metals, a semi-metal, and actual non-metals. So from sodium, this is a period. So up to here, we have metals. This is a semi-metal. Then these are actually non-metals. So the factors for metals will work here. Semi-metal will work here. Then non-metal factors will work there. So you don't mix something at once generally. So we see that from sodium to aluminium, actually we can, even before you look at the graph, the melting points actually have increased up to here, from sodium to silicon. Then they decrease generally from silicon to argon here. But there is a slight increase from sodium to aluminium. Then also there is an abnormal value in silicon here. So you can have a look at that graph there. So we see that the melting points generally increase from sodium to silicon, then decrease from silicon to argon. Then there is an abnormality here. then there is a small abnormality there. So for metals, we are going to look at sodium, magnesium to aluminium. We are going to look at the factors for metals, which are atomic radius, then number of electrons contributed to the metallic bond. Those two factors, they are very, very important. Sodium is in group 1, contributes 1 electron. Magnesium contributes 2, aluminium contributes 3. But also the size, the radius decreases from sodium to aluminium. That accounts for the increase in the strength of the metallic bond. But this slight increase from magnesium to aluminium is just that there is a decrease in the metallic character because we are traversing into semi-metal, then non-metal. So aluminium has a less metallic character than magnesium. That's why the metallic character has decreased here. That's why it makes a slight just increase in the melting point here. Now in silicon, we say the factors there are actually the type of structure they have, like this one has a giant atomic structure. That is the key point for this semi-metal here. Then for these non-metals, actually sulfur is S8, S8, phosphorus is P4, then chlorine is CO2, argon is AR. So you see that if you calculated the molecular masses with respect to these molecules, sulfur would actually be having a very high molecular mass compared to phosphorus, and phosphorus to chlorine and argon respectively. So the factors are molecular mass, then the molecular mass and the strength of the van der Waals forces. You can look at the answer. So generally, the melting point increases from sodium to silicon, followed by a general decrease to argon. Sulfur has a higher melting point than phosphorus. Then you say sodium, magnesium, aluminium have giant metallic structures. Mention this point because this table is a mixture. Then we are saying that the number of electrons is very important, and also the atomic radius here is very, very important here. So sodium contributes 1 electron, magnesium contributes 2, aluminium contributes actually 3. So the metallic bond increases like that. Then the metallic bond strength increases from sodium to aluminium, but there is this slight increase here due to the decrease in the metallic character there. Silicon has a giant molecular structure in which each silicon atom, you describe that. That is the tetrahedral structure that is similar to the structure adopted by carbon. This structure is what we're talking about here. The bonds that are in silicon are like that. That is the structure we are talking about there. Phosphorus, sulfur, chlorine, argon have simple molecular structures. Mention that. Very key point. Sulfur is octaatomic, has S8 rings. Phosphorus is tetraatomic. Chlorine is diatomic. Then argon is monoatomic. So if you calculate the molecular masses, they will be actually varying with respect to the molecule. Sulfur would be higher than phosphorus, and phosphorus would be higher than chlorine. Then chlorine would actually be higher than argon there. Now let us look at question 4. Question 4 basically is under group 2 elements. So the question says the graph shows the melting points of group 2 elements. State and explain the trend in the melting points of the elements. Now, since we are only in group 2 and all are metals, so we are going to engage in the factors that affect the melting points of metals, which is atomic radius, then number of electrons contributed to the metallic bond, number of electrons. Then factor 3 is the crystal structure. But factor 2 will not work because all of them are in group 2, so they have 2 valence electrons. So number of electrons contributed are the same. So the key factor is atomic radius and the crystal structure. Let's dive into this. Now we see that generally the melting points are actually decreasing down the group from beryllium to barium. Now factor number 1 about atomic radius is the one which is coming into play, because from beryllium to barium atomic radius increases, so it means the bond length increases and the bond strength reduces. But we can also learn that there is an abnormality between calcium and magnesium. We expected magnesium to be about at this point here, but slower than calcium. There is a reason, and that will be explained in the crystal structure. Now we realize that beryllium has a structure called the hexagonal close pact, so HCP, hexagonal close pact structure. Then magnesium has also hexagonal close pact. Calcium has two structures. In solid state, it has face-centered FCC, and when you melt it, it goes to another structure called BCC, body-centered cubic structure. Then these ones, strontium and barium, have body-centered cubic structure. Remember, we say the elements which have HCP and FCC have a packing efficiency which is the highest compared to BCC and simple cubic structure. So we can dive into this and see that the calcium will change the crystal structure. So transiting from FCC to BCC causes its melting points to go high because there is need to break to convert from a more stable structure to a less stable structure here due to change in the crystal structures. So let's look at the answer. So we are saying the melting point decreases from beryllium to barium. Reason: atomic radius increases, bond length increases, metallic bond strength reduces. Now magnesium and calcium have different crystal structures. That's why magnesium actually has a lower melting point than calcium, because magnesium retains the hexagonal close packed structure in both solid state and liquid state. So when you heat magnesium to melt it, the structure is still HCP. However, in calcium, you see that there are two crystal structures. It is FCC, very stable, and it's now transiting to BCC on heating. So that kind of energy required to overcome a more stable structure results into a higher melting point. So let's look at the next question here. This is now in group 4 elements here. So I have carbon. So from here up to here, this is a non-metal, semi-metal, semi-metal. But they all have what we could call giant molecular structures or giant atomic structures, so which are similar to carbon structure like this. So carbon, they all have tetrahedral arrangement of the atoms like this, these three here. Now these adopt giant metallic structures here. So these will be explained according to, so the factors are going to be a mixture here. So we have atomic radius for all same metals. We have atomic radius. We have type of structure that they adopt there is also very, very important there. So we are going to see that carbon, silicon, germanium have giant atomic structures. However, because of the increase in the atomic radius, the covalent bonds in those structures actually become weaker from carbon to germanium. In silicon and lead, we are saying that lead is more metallic because of the large atomic radius and being more electropositive, and due to has the inert pair effect there. So silicon here, being large atomic radius, is less metallic compared to that. So you can look at that. So melting points decrease from carbon to tin, then increase slightly from tin to lead. Reason: carbon, silicon, germanium have giant atomic structures. Tin and lead have giant metallic structures. Now the difference between carbon, silicon and germanium, same structure, but because of atomic radius, they are going to actually, the bonds in those structures will actually vary in the strength here. So I hope that one can be captured well. So melting point increases slightly from lead to this. The reason is increasing the metallic character, increasing the metallic bond strength. We say the reason is the inert pair effect, and 2, metallic character. Because as atomic radius increases, electropositivity increases, metallic character actually increases there. Let's look at number 6 here. Number 6 is basically the oxides of group 2 elements here. So all of them are ionic. So we are going to look at factors affecting ionic compounds only, which are ionic charge, ionic radius, then polarizing power effects here. We see that beryllium here has a value lower than magnesium, but actually there is a decrease from magnesium oxide to barium oxide. So there is some abnormality in beryllium oxide here. So we are saying that from beryllium has a lower value. Reason we are going to give it here. Melting point increases from beryllium oxide to magnesium oxide, then decreases from magnesium oxide to barium oxide. Or we can say melting point generally decreases from magnesium oxide to barium oxide. However, beryllium oxide has abnormally lower value. So the decrease from magnesium oxide to barium oxide is actually dwelling in the factor that we talked about, the ionic radius, and which affects when the radius from the ions, magnesium ion, calcium ions, strontium ions, and barium ions, actually their cationic radius is increasing down, because cationic radius varies the same way like ionic. Cationic radius varies the same way like atomic radius. So because of the increase in the cationic radius, that makes the bonds, the ionic bonds, not the metallic bonds, to become more longer and weaker down the group. So in beryllium oxide, the reason is the beryllium ion is very, very small. So high polarizing power, high charge density, and predominantly covalent. A compound which is more predominantly covalent is actually thermally unstable. Let's dive in number 7 here. We are looking at the boiling points of the hydrides of group 7 elements. So we are required to plot a graph. So let's look at the graph here directly. So on plotting the graph here, we see that the boiling points actually decrease from HF, hydrogen fluoride, to hydrogen chloride, then increase from hydrogen chloride to hydrogen iodide here. Now, since these being covalent compounds, we are going to use the factors for covalent compounds such as molecular mass, intermolecular forces, where there are now 2 hydrogen bonds, and van der Waals forces here. Like we are seeing that fluorine is more electronegative. The rest, chlorine, bromine, iodine, are less electronegative. So HF would be more polar than all of them, making HF to actually have hydrogen bonds. The rest will actually have van der Waals forces, because the polarity is not strong enough to result in hydrogen bonding in these ones here. So we are going to explain the increase from HCl to HI in terms of the molecular masses. Like if we calculated the molecular mass of HCl would be 36.5, HBr would be actually like 81, then HI would be actually like 128. So we are seeing molecular masses are increasing here. Despite HF having a low molecular mass, but it has a stronger force called the hydrogen bonds, which are stronger than the van der Waals forces here. Let's dive into discuss and we see. Boiling points generally increase from hydrogen chloride to hydrogen iodide. However, hydrogen fluoride has abnormally high value. Or we can say boiling points decrease from hydrogen fluoride to hydrogen iodide, then increase from hydrogen chloride to hydrogen iodide here. The increase we've already explained, from hydrogen chloride to hydrogen iodide. The increase is actually in terms of molecular mass, and being that all of them are gases, some are HCl is a gas, all of them are gases, that mandates them to have simple molecular structures here. Hydrogen fluoride has abnormally high value because it has a high electronegativity, small atomic radius, making the hydrogen fluorine bond polar, so it has intermolecular hydrogen bonds there.